Okay, good morning, everybody. So, at the outset, let me thank the organizers for giving me this opportunity to present my work. So, I am going to tell you how to hunt primordial black holes in the Lyman-alpha forest. And this is based on a recent work that just appeared in archive just last week. So, feel free to go through the paper. And let me first acknowledge people with whom I have done this work. So, this is done with Ranjan Laha, who is sitting at the last row, who is my PhD supervisor, Priyank Parashari, who is now a postdoc at the University of Southern California, and Akash Kumar Saha, who is a fellow graduate student at the ISC with Ranjan. Okay, so let me first give you a bird's eye view of what I'm going to tell you about. So this should, orient you, where we are going. So if dark matter is made of primordial black holes, and if those primordial black holes emit Hawking radiation, the Hawking radiation can heat up the intergalactic medium a little extra over and above what other sources would do. Now you go and measure the intergalactic medium's temperature. Somehow you measure it, and there are two possibilities. If you find that the intergalactic medium is heated up a little extra over and above your expectations, then you can go and ask the question whether that extra heating has been caused by the primordial black holes. But if it has not been heated up extra, but evaporating primordial black holes would have heated up, so you can just constrain the primordial black hole abundance. So this is a single slide summary of my talk. Now let's get into the details. So this is, I'm sure almost everybody in this room has seen this picture hundreds of times. This is the pie chart of our ignorance, and around 27% of the energy density of the universe today is unaccounted for. Gravitationally it behaves like matter, but we don't know what it's made of. And there are various possibilities. One of the possibilities is that it's made of primordial black holes. So what these are? So these are just black holes that were formed very early in the universe. The most popular mechanism of their formation is that the very high matter over densities would have directly collapsed to form black holes. But there are some other mechanisms for their formation also, several of them. And depending upon the mechanism, they can be formed having a wide range of masses, and they can have non-zero spins also, technically. Okay, now a little more about them. They would be moving non-relativistically today, since they redshift just like matter, and except for gravitation, they would have hardly any interaction with the baryons, and for high enough masses, they could be stable over cosmological timescales, and they would contribute to the baryonic matter density today. So of course, this smells like dark matter, and yes, there are models which predict that they form in the right abundance to form a substantial part of the dark matter density today. So it turns out that all black holes have a temperature. This is the famous result proven by Hawking, and so this is the temperature that's associated to every black hole. And the important thing to note is that the temperature of a black hole is inversely proportional to its mass. This is when the black holes are not spinning, the non-spinning and uncharged case. And Hawking tells us that these black holes will evaporate, in the sense that they will emit all standard model, and if there are BSM particles, all those particles would be emitted with the spectrum. And what the spectrum looks like? So it is mostly a black body spectrum, except for these factors, and these are called the grey body factors. Now they come into picture because a black hole, the space-time is curved close to the horizon of a black hole. It's exerting gravitational force, and when a particle is Hawking emitted, so the wave function of the particle experiences scattering in the curved space-time of the black hole. So basically, the particle can be re-emitted back into it, can be attracted back into the black hole. So we have to account for these factors also. These are called the grey body factors. And since it's a scattering problem, they have to be evaluated numerically. And this we did by using this publicly available code called Blackhawk. And yeah, so let me tell you that this expression for the spectrum is valid only for the black holes which are not spinning. When they are spinning, then there's slight change in this factor, and this gray body factors also start to depend on the spin of the black hole. So yeah, but we calculated these gray body factors both for spinning and non-spinning black holes using the same code. Now, what Hawking radiation does to the intergalactic medium temperature? So, since we are injecting some possibly high energy particles, and neutrinos would also be emitted, but they are not efficient at depositing their energy, and we need to consider only photons and electrons and positrons which are injected into the intergalactic medium. And it turns out that when these particles are emitted into the IGM, they, several processes happen, atomic as well as, so the heat is deposited over cosmological timescales, and we have to actually, work out what happens to the temperature of the intergalactic medium. So what we have to do is we have to solve these two schematic equations. So the rate of change of the temperature of the intergalactic medium is given by whatever would be if you don't inject anything extra, just the adiabatic expansion of the universe. And if you are injecting extra energy due to primordial black holes or anything else, and because at some point stars also start to form in the universe, and they would also start to inject photons into the intergalactic medium. So this is the rate of change of temperature due to reionization. And similarly, there is this differential equation for the ionization fraction of the gas in the IGM, because all this energy injection due to the primordial black holes as well as reionization sources, this can ionize the IGM also. And these two are coupled differential equations that have to be solved in an expanding universe. So this is done using another code, publicly available code again, called dark history. So we use these two equations. We solve these two equations using dark history, assuming that this extra exotic energy injection is coming from the spectrum of the primordial black holes. Now we have to go and measure the temperature of the intergalactic medium somehow. We know, we should know that how its temperature should change in the presence of evaporating black holes, but how do we go and measure the temperature of the gas? So we make use of this Lyman-alpha transition, which is the most ubiquitous transition in the neutral hydrogen atoms. This is just when electron transitions between the principal quantum number 2 and 1. Yeah, so because of this spin orbit coupling, it's actually a doublet. So yeah, these are some properties of this line. So how does it help us? So suppose there is a distant quasar at some high redshift 6 or something. So quasars have a very broad spectrum. As the light from the quasar comes to us, so if there are clouds of neutral hydrogen in between, I say clouds because reionization also starts at these epochs, and hydrogen, in some regions the hydrogen gets ionized, and in some regions there are clouds of neutral hydrogen. So as this light passes through the clouds of neutral hydrogen, because it gets redshifted as it goes along, we will see this absorption lines due to the Lyman-alpha transition. And it turns out that the width of these absorption features contains information about the temperature of whichever cloud is causing that absorption line. So by looking at analyzing this spectra, people have been able to find the temperature of the intergalactic medium as a function of redshift. So this is just to show you how the spectrum actually looks like. Just focus on this lower spectrum. So as so this is a quasar at redshift 3.62, and as its light come to us, it sees all these absorption lines due to the various clouds that are in the intervening region between the quasar and the observer. So now what are the results? So on the horizontal axis, I have the redshift, and on the vertical axis, I have the intergalactic medium temperature. Now all these data points are the measurements of the intergalactic medium temperature using the Lyman-alpha spectrum analysis techniques. So these different colors are due to the different data sets that we use, and so focus only on this, don't focus on this faded data points. This is something that were actually present in the data set, but we neglected them because either they were in tension with some other point, for example this one, and in this region we don't take into this because when we solve the temperature and ionization coupled equations, we have to keep in mind that I showed you the ionization differential equation also. That was assuming that there's only hydrogen in the intergalactic medium. Now, below these redshifts, helium also starts to get ionized, and so we don't know how to handle it. So we work only till here. Okay, so these are the temperature measurements. Now, what is this red curve? This red curve is the temperature of the intergalactic medium that's predicted by some reionization model. Now, we don't completely understand the processes of reionization. There's wide uncertainty in how it actually proceeds, but this curve only shows that there can be a reionization process which completely explains all these temperature data points, which is to say that actually we don't need primordial black holes to explain these temperatures, and hence, you know, we don't claim a discovery of these black holes. We can only put a constraint on their existence. And this is to illustrate what happens to the intergalactic medium temperature if we have a primordial black hole dark matter. These primordial black holes, each of them with mass 10 to the 16 grams, contribute only this 5 times 10 to the minus 3. You know, this is the fraction of the dark matter density that's contributed by primordial black holes of this mass. Now, if we put these also into the mix, they would inject extra energy by Hawking evaporation over and above the reionization energy that's injected, and then the temperature as a function of redshift would look something like this, which means that this model is ruled out. So we carry out, you know, this, we compute all this for various primordial black hole masses as well as various densities, energy densities of the dark matter that they should be contributing to, and we get constraint plots. So on the horizontal axis, I have the mass of the primordial black hole. On the vertical axis, I have this parameter FPBH, which is just the fraction of the dark matter density that could be contributed by primordial black holes of this particular mass, assuming a monochromatic mass function, that is, all the primordial black holes are given by this mass only, there is no distribution. And so these are the constraints that we obtain. So what are these bands? So this red colored band that you see on the top, this is plotted assuming that the reionization sources are not heating up the intergalactic medium, and hence this is very narrow, because then we completely get rid of the uncertainties associated with the process of reionization. But this blue colored band, this is when you assume that there is heating due to reionization also, and hence there are uncertainties associated with that process, hence this band is a little broad. But these constraints are weaker, the one above the top, this red colored band, but they are very robust, because whatever happens to reionization, these are not affected at all. And this is for black holes which are spinning, so their dimensionless spin parameter is equal to 0.99, and this is the exact same plot which is for the black holes which are not spinning. So these are the constraints that we obtain, and both of these figures, these other lines show the constraints that are obtained by some other techniques. So, but this is the first time that these Lyman-alpha measurements have been used to put constraints on the existence of primordial black holes. So this is all I had to say. I would just summarize that primordial black holes are black holes that could have formed very early in the universe, and Hawking evaporation of these black holes could lead to direct and indirect consequences, giving us the only way to search them, because these are very light, so there's no other way to look for them. And Hawking evaporation spectrum, we computed the Hawking evaporation spectrum and utilized it to calculate the evolution of the intergalactic medium's temperature. And the temperature of IGM has been measured by people using Lyman-alpha spectroscopy, and just by comparing the temperature evolution of IGM, assuming primordial black holes existence with the measured temperature, we can put limits on the existence of these primordial black holes as a function of what fraction of them can contribute to the dark matter density observed today. Thanks.
Other questions? Yes. Okay.
Can you explain a bit more how you arrived at the conservative constraint which was not dependent on the reionization model? I couldn't understand that part.
Okay, so see, you're talking about this versus this, right? So it turns out that, see, this is obtained by just using the free electron fraction as a function of redshift that we directly get from Planck. But the T dot term in this differential equation, yeah, this is switched off. Whereas in this, for example, this, this. So yeah, there are three colors. That's a bit confusing. That's just an artifact of the, how Matplotlib plots these colors. But the broader thing, we have the T star dot term switched on also. So that has a lot of uncertainties, which, astrophysicists tell us and we just take them or else.
So could you just go to, I think, slide 14 or 13? I know 15. This one with it's, when you discard data, I could make another choice and say discard the green points.
With this one?
Yeah.
Yeah, okay.
So did you try choosing a different data set, or even how bad is the fit if you keep everything?
No, I'll tell you. So the reason that this is discarded versus this is that if we take this, we get conservative constraints. If we had simply used this, our constraints would have been much stronger. So just in, we are just trying to be conservative in our limits. For example, this is, so the temperature of this point is lower, right? So
yeah, I don't like this terminology of conservative. I consider myself a liberal, but I understand why it's done. But I think it's important information, because clearly I agree those points are in tension. What are the dominant uncertainties on these measurements that are going in?
Yeah, so there are several of them. So first of all, there's uncertainty that's come directly from the fact that how well you can resolve all this, lines that in the spectrum. And yeah, secondly, it turns out, that to infer these temperatures, you have to compare these, you have to generate mock spectra of Lyman-alpha forest. And that is done using simulations. So the simulations themselves come with their own set of uncertainties.
Okay, it's interesting. Thank you.
If you keep the faded dots and remove the dark green ones, and you take 60% of your green line, then it will go through all your data points.
Sorry, I didn't understand.
You have your, what is it called? PBH with photo heating model. Look at that green line, right?
Yes.
Because it's all green. I can't help you. I mean, so if you just lower that by exactly 60%, then it will go through all the points except the green dots.
That's called cooking up.
Sorry? So I mean, it's like little dangerous to kind of decide. Please, I would be very happy.
Rahat.
Sorry, Abhijeet knows this, but let me repeat. So we talked to lots of, at least Prakash Gaikwad, who is a Lyman-alpha expert. He has done some of these things. We asked him why is this difference. Even he does not know this. So I think this is why this redshift 6.5 is doing weird things. As far as we know, we also asked, I think, Vikram Khaire. I think he also doesn't know the answer. So I think people who have done these measurements, they don't know the answer. And that's why
I don't know whether this is correct or this is correct.
Nobody knows that answer.
We are choosing what gives us the conservative limits.
And if you see the simulations, as he showed, there is one solid line and then there is dotted and dashed lines. They are sort of the envelope. All of them go through everything. And then we are sort of stuck with, we don't know what to do. And then, according to Prakash, if I do new physics, the best thing is to do the conservative case and just move forward. Yeah, but good. But you see, I take your point. So we can discard this redshift bin, but but higher redshift has more dark matter density, which should help us. So yeah, in some sense we could have just discarded that one thing, but there are two other things. Yeah,
It's tricky.
Yeah, I agree.
So we have exactly the same situation with G-2 and
Yes.
this cross section. At the moment, we do nothing with them because we can't average
Yes,
them. We
yes.
have to figure out what's wrong.
Yes. Okay. Thanks. Yeah. So,
I have a small question.
yes.
Primordial black holes which you have, the masses are much, much less than the sun's mass itself, right?
Yes.
Probably it is,
Yeah,
size,
these are the masses.
yeah, the size will be too small.
Yes.
Is it reasonable to consider, because people consider slightly higher, at least sun's mass?
No. So see, So you're talking about astrophysical black holes, but yeah, these can be as light as you want to. In fact, this lower limit comes also into the play just because these primordial black holes of these masses would have already evaporated away. But technically, if you go to the primordial black hole formation models, they can predict very small black holes also.
Okay. Okay. Thank you. Last question.
Sorry, I don't understand. So this, what is excluded here? Is that only the blue band and everything?
So all this region is excluded. So that the line above which everything is excluded is uncertain depending on what you do with your reionization. But for example, this region is certainly excluded, and here you have to do some reionization modeling to exclude this region. So anything that's above this line is excluded. So for example, a primordial black hole of 10 to the 16 grams. So these black holes cannot contribute more than, let's say, 10 to the minus 4 of the total dark matter density.
So then why is there a dark blue band?
Yeah, that's because of the uncertainty in the reionization processes.
Yes.
So reionization T star dot term that I showed, this term is not known at all. I mean, yeah, there's a very, the uncertainty in this term is huge.
Got it. Yeah.
Thank you. Let's thank the speakers.